Welcome, everyone, to the Cultivating Compassion Education series, sponsored by Compassionate Care ALS. We're fortunate tonight to have Dr. Dan Rubin with us to speak about Braingate. It's exciting new technology that he's been working on for several years and that Mass General has been researching for quite some time. Dr. Rubin is a neurologist and researcher at Massachusetts General Hospital and an instructor in neurology at Harvard Medical School. Dan joined the Braingate team in 2019. His research interests are focused on understanding the dynamics of neural coding to develop electrophysiologic biomarkers and tools to facilitate recovery after acute and chronic neurological injury. Dan received his MD and PhD in computational neuroscience from Columbia University studying circuit mechanisms of information processing in mammalian cortex, and completed his neurology residency and neurocritical care fellowship at Massachusetts General Hospital and Brigham and Women's Hospital in Boston, Massachusetts. Welcome, Dr. Rubin. I'm going to turn it over to our founder and executive director, Ron Hoffman. Welcome, Ron.
Yeah, thanks, James. Hey, everybody. Daniel, really happy that you can be with us tonight. I met Daniel some years ago when he reached out, and I went up to, actually we did a Zoom. I might have gone up once, but we did a Zoom call. The work that Daniel's going to share with us tonight has been going on for a long time. And when he showed me what they were doing, I was amazed at how far it had come. It's like science fiction on some level. It's extraordinary. Myself and Christine, who many of you know, is our communication guru, as I like to call her. We got to experience this work many years ago with several of our clients who partook in this study. And boy, it has come such a long way. So I'm going to turn it over to Daniel. Dan, thank you so much for being here. And this is going to be very interesting. So thank you, Daniel.
Well, thanks, Ron. Thanks, James, for the kind introduction. Thanks, everyone, for joining tonight. I know it's kind of late, so I appreciate you spending some time with me today. I'm going to share my screen because I'm going to show some videos and some movies as we go and explain what we're doing. And I'm going to presentation mode. That'll work. There we go. Now, I can't see any of you anymore because I'm looking at my slides, but please do reach out if you have any questions, either put them in the chat or interrupt me. And I'm going to tell you about Braingate. And as Ron said, Braingate's been going on for almost 20 years now, about 18 years. And the goal of Braingate is to develop brain-computer interfaces to restore and maintain communication, mobility, and functional independence for people with ALS. And I'll tell you a little bit what that means to start with, such as we do with any of these scientific talks. Quick disclosures. So we don't have any proper financial disclosures. We are a non-for-profit academic consortium made up of researchers at universities around the country like myself. None of us are part of a company, but we do have lots of support from nonprofits, supports from philanthropies, and from, in particular, the federal government. And so we're thankful for all of that. So what is Braingate?
Dr. Rubin, real quick, there's a kind of a black bar on the screen that's blocking your slides a little bit.
Let's see if I can get rid of that. How can I?
There you go. Okay, it's off of there now.
Oh, is that right? Okay, good. What if I put it up there? You know what? I'm going to put it down here. Is that better?
Yeah, it's fine. Yeah.
Oh, great.
Yeah,
okay.
Good.
So I'm going to tell you a lot about what Braingate is, but I think it helps to start by telling you why Braingate is, in a sense. So what are our goals? And they're pretty straightforward. So what we want to be able to do is for anyone with ALS, muscular dystrophy, any other motor neuron disease, people who might be facing a future where they're not sure if they're going to be able to communicate. We want to be able to tell them that with this technology, you will never lose the ability to communicate. And when we say communicate, we mean communicate easily, fluently. And we'll talk quite a bit, or I'll talk quite a bit about what specifically we mean by that. For people who yesterday could communicate, but then because of something like a stroke, if they wound up in a locked in state, LIS, we want to be able to tell them they're going to be able to communicate again easily tomorrow. And for people with spinal cord injury, stroke, or people with ALS who are losing the ability to move, we're going to be able to move again tomorrow. Now, these are our goals. We're not there yet, but this is where we'd like to be. And I think, as I'll be able to show you over the course of the evening, we're getting pretty close. So before I dive into Braingate in particular, it's helpful to set up a little bit of a framework and describe what brain-computer interfaces, or BCIs, are in general, because all brain-computer interfaces have the same basic framework. And the idea works something like this. In a condition like ALS, we know that progressive weakness occurs because of injury and loss of the motor neurons, the connections between the cerebral cortex, the brain, and the muscles. But in ALS, the cerebral cortex, the part of the brain that we think about as really what makes us us, that gives us the ability to generate movement, intention, personality, thoughts, that's intact. That works just fine. It's the connection between that cerebral cortex and the muscles that gets affected. And so all brain-computer interfaces start with a sensor, something that's listening to the activity of the cerebral cortex. And here's a diagram of a typified cerebral cortex. And when one is designing a brain-computer interface, you have to decide, well, what kind of sensor are you going to use, and where are you going to place it, and what are you going to try and measure? And so these are the sort of questions that come up. And I'll tell you the decisions that we've made. There are other types of brain-computer interfaces that use different types of sensors and listen to different signals. Once you've got your sensor and you're listening to the activity of the cerebral cortex, the part of the brain that's perfectly intact and works just fine, then you need to decode that. So the brain communicates with itself and with the motor neurons and with the muscles through electrical impulses, but it has a unique code, something that we neuroscientists have been spending the last 60 years trying to crack. We're getting better and better, but it really is a foreign language. And so we develop mathematical decoders that attempt to translate that activity that we're measuring into some sort of intention, into some sort of meaningful signal that we can then harness. And so here we've got a sort of typified equation that's describing what that decoder might be. And this is just matrix algebra. But in reality, these decoders, when we're actually using them in the technology, are thousands and thousands of lines of computer code that harness state-of-the-art artificial intelligence and machine learning algorithms that attempt to relate some high-dimensional signal, as we're recording from hundreds of brain cells at once, with some lower-dimensional output. And that lower-dimensional output is an electronic signal that we then pair with some form of assistive technology. And this is the part of the research that is sort of the most exciting, really, because this is where we get to take all of this great neuroscience and engineering that's been going on over the past half a century and really make it work for people. And I'm going to be showing you some of the different technologies we use, but this is where we really let our imaginations run wild. How can we use this technology to make someone's life better, to restore function that's being lost, and to give people increased mobility, independence. And then we're not there yet, but there's this notion that in the future, we may be able to close the loop and even try and restore some of the brain's endogenous function by closing the loop and sending a signal back into cortex. And I'll hint a little bit of what that is, but we're not really there just yet. So the first question, as I mentioned, is what sort of sensor do you use? You can record brain activity in a number of different ways. Many people may be familiar with something like an EEG. That's a brainwave recording that someone might get if they were seeing a neurologist and the neurologist was worried that this person had seizures. And that's something you wear on the scalp. It's it's kind of like an EKG that you might have of your heart, but you put it on your scalp and you measure brainwaves. But those don't get you very high resolution signals because they're recording activity many centimeters away from the brain and through the bone and skin. What we use in the Braingate system was what's called a micro-electrode array. It is pictured right here. You can see it's 4 by 4 millimeters. It is smaller than a Lincoln Memorial on the back of a penny. And this little chip, this 4 by 4 millimeter chip, contains 100 microscopic electrodes on it, arranged here. And this is a scanning electromicrograph, so a picture under a high-powered microscope showing you what it looks like. If you were to hold one in your hand, it looks a bit like almost like a hairbrush that you might see in a dollhouse, for an example. And here's an example of one of those single micro-electrode array electrodes next to a single brain cell. And the key to this sort of recording array is that unlike an EEG that records from hundreds of thousands, if not millions of brain cells at once and gives you an average signal, here you're actually measuring the electrical activity of individual brain cells. And it gives you the ability to really access information that's being processed in cortical circuits in a very unique way. And in fact, when we use this technology now, we don't use one of these arrays, we actually use anywhere from 2 to 4 of them to record from hundreds of individual brain cells at once. So this is a now somewhat old cartoon, but a demonstration of what the actual hardware of the Braingate system looks like. And then we'll spend the rest of the time really talking about the software, what we're able to do with it. So the idea is you've got one or more of these micro-electrode arrays, and here they are again, the same picture I showed you before. They are placed by a neurosurgeon on the surface of the brain and then connected by this gold wire, if you can see my mouse, to what we call a percutaneous pedestal. And so this is a tiny metal piece. It's about, I don't know if you can see, about the end of my thumb in size, and the top is threaded, and that thread is what actually goes through the skin and connects to the Braingate computer system. Here it's done with a cord. We also have a wireless system that's not shown in this cartoon, but I'll show you a little bit later. And so when we're recording the brain's activity, this is an old-fashioned oscilloscope. We don't use these either, but this is just to demonstrate that there's electrical activity. The Braingate system gets attached to this pedestal. We record the brain's activity in real time. This activity gets processed, gets sent to a computer system. So here's a rack of computers. And then the output is really whatever we want it to be. And here we're showing a cartoon of someone using the Braingate system to control the blue cursor on a computer screen and play some imaginary video game that we've come up in this cartoon. And I'll show you a little bit more detail of how it works in real time in just a moment. But this is the general, the idea of how the setup works. What does it mean to be a part of the brain? How does one get involved in Braingate? I'm going to explain this up front because everything I want to show you going forward is part of an ongoing clinical trial. And it's important to know that this is not something that one can just go into the hospital and have just yet. So right now, everyone who has received a Braingate neural interface system thus far has been part of our feasibility study. This is a clinical trial registered with the FDA. And like all clinical trials, there are certain inclusion criteria. So people who we work with are people who have either severe weakness of their hands or severe dysarthria due either to ALS, muscular dystrophy, spinal cord injury, or stroke. It's all adults. For people who had a spinal cord injury or stroke, it has to be a year after the time of their injury. People need to be healthy enough to undergo the surgery to have the device placed, and they have to live close enough to us within 3 hours so that we can work with them. And the reason is that all of the actual research occurs in our participants' homes. And this is something that we think is sort of unique, but really important to the mission of this research. And so, lots of research occurs in university or hospital laboratories, but the point of this technology is that we're trying to develop tools that are going to help people in their home. And so we need to make sure that this works in the home. If we ask someone to come into the lab twice a week to take part in research studies, it wouldn't really tell us very much about how this technology could be used to really help people who need to use it. For anyone who's interested, we are recruiting. I'll talk a bit more about that a little bit later. And another thing just to talk about is sort of what does the research look like? What is the research focus? So it is a clinical trial, but it's not a sort of typical placebo-controlled trial for something like a new medication. And what we mean by that is that the goal of this research is really translational, how to take all of the engineering and neuroscientific achievements that we've reached over the past, again, 50, 60 years of research and bring it to people to be of use to them. And so there are some things we do to really make sure that this is research that's focused on our participants. So for one, we use broadly defined inclusion criteria. So there's no placebo groups, of course. No one who enrolls in our trial gets a sham device or anything like that. When you set up a clinical trial, one of the things that the FDA always asks you is, well, how long is the trial for when you evaluate your endpoints? And so you have to say something. And so we say, well, we're going to evaluate the endpoint at 1 year. But many people then ask us, well, if I'm really enjoying using this technology. If this works very well for me, do I have to give it back at the end of that 1 year? We said no. So anyone who joins us in the clinical trial is welcome to continue working with us for as long as they'd like to. At the end of the 1 year period, we pause, we say, do you want to keep going? And virtually all of our participants have said yes. And some people have actually continued working with us for more than 5 years at this point. An important point, particularly with regard to the ALS community, is that people with advanced disease are not excluded. So as I suspect people on this call know, for certain clinical trials, particularly for things like disease-modifying drugs, once someone has advanced past a certain point, they may not be eligible to participate because the point of many of those trials is to demonstrate a slowing of disease progression. But in contrast, in our study, no one is excluded based on advanced disease. And as I'll show you in some of the videos, people with advanced disease using a ventilator 24/7 have been welcome and enrolled, and really been fantastic participants and really accelerated the research through their working with us. And as I mentioned, all the research occurs in our participants' homes. A couple of years ago, you couldn't really go into the people's homes for a few months, year or so. And we developed the ability to actually conduct remote sessions. And so we can actually do research sessions now, even without being in our participants' homes. And I'll talk a bit more about what that means. And a big part of the research is that we have certain goals that we're trying to achieve in the research, making sure that the system works well, that it's safe, that people are able to have robust control of what we consider to be some of the core goals of the research, things like communication mobility. But we also interact frequently with our participants, and each one of our participants really brings a lot to the research sessions. And so they say things like, this is really great, but what would really make my life much better or my home more comfortable would be if I had the ability to control the smart electronics in my home, to control the lights, or to be able to interface more with this computer system or that computer system. Or it would be really fun if I could create music. I'd love to use this with a home music generation system. And we listen to those, and we emphasize research sessions that our participants tell us are important to them. All right, so that's the background. Now to show you some examples of how the system works. So this first video I want to show you is actually from our very first participant who joined our trial with ALS. So this is now about, I think, 14 years ago or so, and you'll be able to tell from the video that some of the technology looks a little bit outdated, and that's an important reason. You'll see that. And what I'm showing you here, and what you're probably hearing, sounds a little bit like if we're trying to tune an AM radio and we're in between stations. It sounds like static. And if you're trying to tune your car radio, you don't want to hear static. You want to hear the news or sports or weather. But if you're recording for brain activity, this is exactly what you want to hear. And we were very excited to hear this when we started working with participants with ALS, because there was some concern from some of our colleagues that we weren't going to be able to get really good recordings because there was concern that the neural activity wouldn't be there in someone with advanced ALS. We said, no, we're recording from cerebral cortex. This should work just fine. And sure enough, we got great recordings. In fact, robust recordings that look as good as recording from someone who doesn't have any weakness. And what you're seeing in the corner, and I'll expand out from here for you, this is that same participant who has advanced ALS. By the time he joined us in the trial, he was using a ventilator 24/7 and was unable to use his arms to talk. But here he is being asked to move a computer mouse to the yellow square. And we basically said, imagine that you've got your hand on a computer joystick and go up, down, left, right. And you imagine moving your hand as if you're controlling a joystick. We'll interpret your brain's activity for those intended movements, and we'll translate it into control of the computer mouse. And sure enough, he's able to do it. If you look at it, it's a little slow, it's a little inaccurate, but this was, again, about 14 years ago. And we've gotten better. So this is now, fast forward about 10 years. This is 2016. You can see the computer monitors are bigger, the video is smoother. And here is a participant using that same sort of approach. Imagine moving your hand to control the little white cursor. And here the goal was move the white cursor to the red circles as quickly as you can. And then once you get there, imagine clicking. And the way that we instructed him to imagine clicking was by squeezing his hand. And sure enough, he's able to do that. And you can see he's able to do it pretty quickly. And of course, you can imagine, once you've got control of a computer mouse that you can click, well, then you can type on a virtual keyboard. And so here we've asked that same participant, will now copy a message. We'll tell you the sentence that we'd like you to copy, and just use this computer mouse, this virtual mouse, to type. And he's able to do that. And you can see it's reasonably accurate and it's reasonably smooth. It's perhaps as good as some of the other technology that's out there nowadays for controlling a mouse without control of your hand or fingers. And we said, well, this is pretty good, and this is a pretty good first step, particularly for someone who's got difficulty communicating. But if our goal is to make this fast, smooth, fluid, something that you could use to communicate on an everyday basis, we need to make this better. How can we make this better? And so that brings us to our first goal, which is using this technology for communication. So the first way we said we could make this better would be, well, what if we just made a better keyboard, right? There's no reason to use a QWERTY layout keyboard if we're controlling it with a virtual mouse on a screen. So let's just put all the letters that we typically use close to each other. The other thing, of course, we did with each step of the way was to use faster computers and better decoding algorithms. I mean, computers have come a long way in the past 20 years, as you all know. And so here's a participant who also has ALS, is unable to use her hands and uses a ventilator 24/7. We've asked her once again just to copy the sentence up above using this virtual keyboard. And you can see we put the letters that one would typically use more frequently, like T, H, and E, A, in the middle of the computer keyboard. And with that, she's able to type at about 40 characters per minute. And that's pretty good. That's reasonably fast. That comes out to about 8 words a minute, which is on par with a lot of the eye gaze technology that's out there right now. Importantly, this is done without any word prediction. As anyone who's used Gmail or any web-based word processor at this point knows, usually you write the first letter or two of what you're trying to say, and in no time, the computer knows what you're trying to say and fills in the rest of the word, sometimes even fills in the rest of the sentence. And so we said, well, this is very good, but there's all this great technology out that can already do autocomplete for sentences and words. So rather than designing our own keyboards and our own assistive technology, what if we just use the Braingate technology and gave people control of off-the-shelf, unmodified commercial computer software, computer hardware? And so here are 2 of our participants. In fact, these are the 2 participants who I've already showed you in 2 prior videos. The woman on the left was the one using the optimized keyboard in the prior video, and the gentleman on the right from 2 videos ago, who was, you can recognize the paintings in the background, who was using that accurate point and click control. And here they are both using completely unmodified Google Nexus tablets. And so the one on the left is sending an email in the email app, and the gentleman on the right's searching YouTube. And what you can see is they're just thinking about moving their hands. And as you'd imagine with either of these websites nowadays, the computer's doing autocomplete. They're able to basically use this technology in much the way one could if you didn't have any weakness. Some things to note, just because we're going to make them better in subsequent videos. They both have what we call our old patient cables. So these are the old connectors that used to connect the pedestals to the computer system, these large block-like cable connectors. We don't use those anymore because the technology has gotten better, and I'll show you that. The woman on the left, she had 1 pedestal. The gentleman on the right had 2, I think you saw. So we can speed up communication by making the keyboard better. We can speed up communication by using things like autocomplete, just to use technology that's already out there to fill in words faster. But we said, well, how can we get even faster? Well, typing on a virtual keyboard is not the only way that people communicate. A lot of people communicate by writing with a pen or pencil on paper. And in fact, writing, by hand is probably faster than typing for most people that aren't professional typists. And so we said, well, we've gotten very good. Everything I've shown you thus far is based on the principle that we're decoding the brain's intended movement of the hand for controlling something like a mouse or computer joystick. But we had gotten very good at this point. This is now 2020, 2021. We've gotten very good at understanding how the brain wants the hand, fingers, and wrists to move. So then we said, well, what if we tried to decode something that's a little more complicated? And so we asked one of our participants, imagine that you're holding a pen or a pencil and just writing out the letters of the alphabet. And we're going to attempt to decode what your brain is telling your hand to do with an imaginary pen or pencil. And sure enough, when we did that, these were the letters that we decoded. So this looks like something that might have been written by someone with a stylus on a tablet PC. But in fact, these are completely imaginary, if you will, letters. These letters were never written by anyone's hand. These letters were written by one of our participants' brains. Now you could say, well, all letters are written by someone's brains, and that's sort of an issue of semantics. Fine. But the idea that each of these letters were decoded from the neural activity of one of our participants who thought about holding an imaginary pen or pencil. And you can see they look like letters well enough that we can then train our computer to recognize which letter our participant's trying to write. And when we do this and ask our participant to copy a text, so here he is in real time reading the message that's on the screen. Imagine he's holding a pen or pencil, and imagine he's writing out the sentence as if he had a pen and paper in front of him. And you can see the letters are coming up pretty fast, certainly faster than a point and click on a virtual keyboard. You can see he's writing out a message here, and this is in real time. So this isn't sped up or anything like that. And I'll go to the next video here. We've asked him a question. The neuroscientists, of course, say, well, what if you're just decoding what he's reading, not what he's trying to write? So, okay, so this is the control for that, to speak scientifically. So here we ask him a question, and he's writing out the answer as if he had a pen or pencil in his hand. And with this, he's able to communicate at about 90 characters per minute. And this is, again, before introducing things like autocomplete or sentence completion. And 90 characters per minute is, just to give you a basis of comparison, that's roughly as fast as someone without weakness can type on a smartphone. So if someone's a fast text message sender, that's about 90 characters per minute, just to give a basic comparison. So we think pretty fast and a pretty smooth and fluid way of communicating, for particularly, in comparison to some of the other tools that are out there, we think may be a way to really create near fluent communication, or at least fast enough to be able to participate in natural seeming conversations. But there's a faster way to communicate. I'm doing it right now. I'm not typing, I'm not texting, I'm talking. And so this is where we're going now. So everything that I've shown you thus far has been based on the notion that we're listening to the part of the brain that normally controls the muscles of the fingers, hand, and wrist. And we're decoding the brain's intended movement of those muscles to either control a computer joystick or a computer mouse, or to write a letter. But what if, we hypothesize, what if instead of listening to that part of the brain, we move our arrays over just a little bit and we listen to the part of the brain that normally controls the movement of the muscles that produce speech, the muscles of the face, the mouth, the lips, the tongue. If we do that, can we begin to decode what someone's trying to say? And so here's some initial data. And here there's a lot of, this is just from one of our earlier papers on this. And the notion here is that we asked some of our participants to try producing different phonemes. And I didn't know what a phoneme was until I got into the space, but a phoneme is the smallest individual unit of speech. You can think of it simplified. Phonemes make up syllables, which make up words. And so in theory, if you could decode all of the phonemes that someone was trying to speak, you could put these all together and decode the words they're trying to say. And we found that we could decode phonemes at around 85% accuracy. There's 42 or 46 different phonemes in the English language, depending on where you divide different similar sounding phonemes. We said, well, that's pretty good. That's just about good enough that we could turn this into a speech decoding system. And so that is exactly what we did. And so I'm going to show you another video here. One of my colleagues, Frank Willett, one of our chief engineers, is going to be narrating a little bit of what's going on, but I'll set it up for you. So this is one of our participants. She has bulbar onset ALS, and she has severely dysarthric speech. She's not an arthric, but the speech that she produces is unintelligible to the point that she doesn't speak. She normally communicates with the residual strength that she has in her hand, but here she's going to try and speak, and she's going to try and say the words that are presented on the screen. The other thing to point out here is that she's got the newer version of the connection. So I showed you those big gray boxes that we don't use anymore, and I said we've we've advanced the technology, and here's what it looks like now. And so these are actually just sort of standard mini HDMI cables. And in fact, the technology has gotten much slicker in that sense, the hardware. And so what we're going to do is listen to the part of her brain that normally controls the muscles of her of her mouth and face, and decode the words that she's trying to speak. And you'll hear as she tries to phonate what it sounds like and what we're decoding. So I'm going to hit play here.
Here's what it looks like in real time when our participant uses the BCI to copy sentences cued on the screen. The sentences were chosen at random from the switchboard corpus of conversational English. Our participant can also use the BCI to express herself. In this video, she's freely answering the question, "What are you proud of?" Finally, we also discovered that our BCI can decode silent speech as well. Our participant preferred mouthing the words like this instead of trying to make vocalizations, which she found to be tiring.
Right, and so in that last video, I'm not sure how much you can hear, but she just mouths the words rather than trying to vocalize, and the decoder works just as well. So we can figure out what she's trying to say just by her attempting to do it, even without actually pushing air across her vocal cords. And with this, we're able to decode not 40 characters per minute or 90 characters per minute, but about 60 words per minute, which is more or less the speed of fluent speech. I mean, I'm a relatively fast talker, and I'm probably talking somewhere between 90 and 120 words per minute, but 50 to 60 words per minute is a pretty reasonable conversational pace. And so this is where we're going with the research. And one of our major areas of focus is making this system work better, increasing the accuracy. We have videos where sometimes the decoder gets some of the words wrong, and we'd like to make it have that happen fewer and fewer times and make sure that this works with more and more participants. But this is one of our big areas of ongoing work. That's where we're at with communication. But I say we've got some other goals. Another goal, of course, is mobility. How can we restore mobility? And there's a couple of different ways that we can use the technology to do that. One of our earliest efforts, when we were really focused on as precise as possible control of the hand and arm, was to be able to use this to control robotic devices. So here's one of our participants. She had a brainstem stroke about 9 years before enrolling in the study, and unable to use her hands or arms, but of course can think about using her hands and arms, and enrolled in our study, had one array placed. And here she was asked to think about picking up that thermos and bring it over and take a drink. And so we connected the Braingate device to this large robotic arm, and she thought about picking up the thermos. And she's sort of being slow and cautious because there's a very large, heavy robotic arm approaching her. But with it, she's able to bring it over and give herself something to drink. This was pretty exciting both for us and for her. This was the first time that she was able to feed herself under her own volition since her stroke, which again was 9 years before she joined the trial. And then this video was about 2.5 years into her time with us. So over 10 years from the time of her injury. One of the other, and I'm going to pause this just for a moment. So one of the other big directions of this research is pairing the Braingate device with something called functional electrical stimulation, or FES. And so in the prior video, the participant was controlling a robotic arm. Here, one of our participants who had a spinal cord injury, left him unable to use his arms or legs, has the Braingate device, but has a second implant, and that's an FES system, functional electrical stimulation. And so, as I'm sure you all know, the way that the brain communicates with the muscles is through the nerves carrying electrical signals, and electrical impulses from the brain through the nerves into the muscles are what make the muscles contract and activate them. And so here what we've done is we've got the Braingate system recording from the cerebral cortex, the part of the brain that generates the intention to move. We decode those signals, and then we pair that with stimulating electrodes that are implanted throughout the muscles in the upper arm and forearm. And with this system, we then ask the participant to imagine moving his arm as if he was moving his arm. We send electrical signals into those muscles, and sure enough, with that, he's able to move his own arm. Now you see there's a large apparatus there. That apparatus is not providing any force. That's really just a safety because he's only controlling certain muscle groups. He doesn't have a lot of the stabilizing muscles that he might otherwise be able to control. So that's basically just to make sure that his arm doesn't fall in a direction that he can't control. But all of the movement that you see, so abducting his arm away from his body, flexing and extending his elbow, that's all under his control. And with that, he's feeding himself for the first time since his spinal cord injury. And so this is an exciting bit of research that our colleagues in the Cleveland Clinic are doing using similar technology. That is the Braingate system paired with this FES. Now, the last area of research that we're really focusing a lot on for restoring mobility is something that we hope is going to be a bit more scalable. So the first robotic arm I showed you that looked like it was, something that might be attached to a rocket ship or space shuttle or space station is very neat, but weighs a ton and costs a fortune and is sort of large and difficult to move around with. And so you could imagine might be a bit unwieldy for everyday use. And then the second thing I showed you requires another set of surgical implants. So where we're going with right now for restore mobility is some new technology that's been developed through one of our partnerships with the Harvard School of Engineering. And these are what we call wearable robotics or soft robotics. And the idea, and you'll see it in a video in a second, is that it's basically clothing that has built-in pneumatic actuators, or if you will, air balloons, that inflate or deflate by control from an external motor that allow the wearer to control the movement around each joint. And so it looks kind of like a hockey glove, but rather than being filled with padding, it's filled with these little balloons. And then as the motor inflates or deflates individual balloons around individual joints, the hand is moved. We've got a glove, which you'll see in this video. We also have an elbow and a shoulder. So if someone is wearing all three, you've got control over really all of the joints in the upper extremity in the arm. So here's one of our participants. This is a participant wearing the glove, and you can see we've asked him to think about closing his hand. There's a sort of neutral position, opening his hand, and then a pinch, sort of a 2-finger pinch, and then a full 5-finger grip. And those are the different positions we've asked him to think about using. And with this glove, he's able to move his hand in those different positions. Now, because of his spinal cord injury, he's basically unable to move his hand at all. He does have power in his arm and his elbow, so he's not wearing those pieces right now. But just to demonstrate how the glove worked, we've asked him to do a simple task here. We've asked him to take these foam blocks and try and move them from his desk into a container next to his desk. And without the glove on, you can see the way that he does this is by basically taking the blocks and using his left hand to sort of cradle them in his right hand. But his right hand doesn't have any power, and so you can see it's sort of frustrating for him to do. And so we do it as a baseline just so that we can demonstrate what he's able to do once he's got the glove on. And you'll see that in just a moment. So you can see in order to get it out, he sort of has to use gravity to get the block out. Now he's got the glove on for the first time, and he's asked to pick up these blocks. And this is the first time he's picking up a block, and he sort of looks at it, he says, oh, I'm gonna pick it up. And he picks it up, moves in, he says, oh. Then he thinks about opening his hand, and sure enough, the glove opens. And once he does that, then he's off, and he says, well, this is pretty straightforward. And he's able to do one after another much quicker. And if you compare the speed at which he can move a certain number of blocks, you can see there's really no comparison. And really the rate limiting factor at this point is not even him, but the timers that we've set on how quickly the glove can move from one position to another, which we can adjust. And so that's really where we're going with Restore Mobility. And we're hoping that within really just a few months, in addition to that glove, we're going to be having our participants doing all three components at the same time. So reaching and grasping, controlling things all around their environment. Then the last bit, and really everything I've been talking about gets at this, but there's just sort of a simple example. And this is the notion of functional independence. And from all of our participants and from people that I know outside of the Braingate trial, as James and Rod mentioned, I'm also a neurologist. And so when I talk with patients and I talk with their families, really the notion that we hear over and over again is anything that one can do for oneself without having to ask for help, that means a lot. And so we think about how this technology can restore someone's functional independence. So a lot of our work is not just focused on individual tools, tasks, but how to integrate the system in such a way that people can use it to do things for themselves. And so one of the big aspects of that is making the system wireless. And so I didn't point it out on the prior video, but that participant was using our wireless system rather than the wired system. And being wireless, of course, is important because if you've connected to the computer system by wires, you can't move around as much. And so we've now developed a wireless system that's used with the pedestal. And so what you see here in the bottom is the pedestal just sitting on its own. Here's what it would look like, or here's what it looks like when it's when that threaded component is coming out of participants, one of the wired connectors. But here we've got this wireless system. This screws on, and once it connects, it automatically turns on. And then once the computer systems are turned on, it's sending signals wirelessly to that computer system so that someone can move around their home while they're using the system. And just to give you a sense of the scale, this is, because it's sort of a cartoon, the barrel of this, if you will, is the diameter of a AA battery. It's a little bit shorter because it's a medical grade, so it's a half the length of a AA battery, but that diameter. And then this large flat part is roughly the diameter and dimensions of a book of matches. And so that's the wireless system. And so here's one of our participants. It's a little bit fuzzy because he's in the foreground, and the camera's focused on his Surface tablet. And the idea behind this, I'll play the video. You're just going to see he's going to be trolling his Windows Surface computer, and he's using it to play Pandora. And the key is that he's lying in his bed. He's got the wireless system on. He's looking at his computer. He's controlling the computer, and he's just playing music. And you say, well, that's sort of quotidian, if you will. I mean, that's sort of an everyday sort of thing. And that's the point, is that he's doing this on his own. Without telling you much about him for the sake of his privacy, but he's a young guy who lives on his own. So when his home health aide leaves for the day, he's on his own. And so if he can now control his Surface tablet from his bed as he's lying there before he goes to bed, that's pretty big for him. And so he's really excited about the technology, and we're really excited to keep working with him to give him more this sort of independence. I don't know how long I've been talking, but I feel like it's been a while. So I'm gonna pause there just to say a couple of things. One, thank you for listening. Like I said, I haven't been able to see any of your faces because I've been looking at my slides, and so but I appreciate you all for being here. If you have any questions, this is my email address, or you can email the Braingate trial. Of course, it's just going to come to me anyway, so you're also just welcome to email me. And this is our website. I'm going to take any questions anyone has now. If you have questions that you want to ask me offline, that you want to ask in front of the whole crowd, please email me. I'd be happy to correspond with you via email or chat via Zoom or phone, however you'd like. And if you want to learn more about our trial, I'd be happy to tell you more about that too. I do want to thank all of you and CCALS for inviting me to give this talk. All of the organizations that are part of this research. So we are Braingate, and as I mentioned, we're made up of researchers from Mass General, Brown University, Emory University, Stanford, UC Davis. Incredible support from the VA system, which is and has been our biggest funder for years, a bigger supporter. And most importantly, this huge team. So these are all of the people at all the institutions. We get together once a year to make this all possible. That's me over there. The guy in the middle, Lee Harper, is my boss, who really started all of this 20 years ago, and just an incredible team of people who are all dedicated to making this a reality. So I will pause there. I'm going to stop slide sharing and hope that I can see anyone who's got any questions and take it from there.
Thank you, Dan. Anybody have a comment or a question?
So Dan, where are you?
Hey, Ron.
Yeah. Realistically, how far away are you from the everyday use of this, from the communication piece for someone with
No.
ALS?
That's a great question. Well, there's sort of two components. There's two ways of answering that question. One is you know, how well does this work without us in the room, right? So for the first 15 years or so of this research, this was a system that would work when one of our research technicians or research investigators was in our participant's home, turning the system on, setting it up. And really in the past 4 years now, we've gotten to the place where we don't need to be there. And so our participants right now who work with us, they can use the system when we're not there. And so we usually show up twice a week to do research sessions, maybe more, maybe less, depending on their priorities and how much time they have to spend with us. But with the wireless system in particular, we can show our caregiver how to attach the transmitter. And then once that transmitter is attached, you turn on the computer system and you're good to go. And so our participants use the technology without us there now all the time. We've got some participants who will do a research session and then we'll say, well, we're done with our research aims for the day and we're going to pack up. And they say, that's great, just leave it running. I prefer this to my head mouse, head tracking mouse, for example. So I'm just going to use this for the rest of the night. And I've got a caregiver who's going to come over in a couple of hours to help me get into bed, and they know how to turn it off. And we say, great. And they can also set it up when we're not there, on days we're not there. And so we've got people who can use this now for communication. The broader question is how soon until anyone can use one of these. So the goal is, when does this leave research and become something that your neurologist or your physiatrist or your physician can just prescribe for you. And there, I think 3 or 4 years ago, we might have been looking in the 5 to 10 year range. But I think with the landscape changing, I mean, I'm sure everyone on this call is, paid a lot of attention to a lot of the news. We're not the only people doing this sort of research. And so there's a lot of interest in bringing this from the research sphere to the clinical application sphere. I can't make any guarantees, but I wouldn't be surprised if there was something that had, preliminary FDA approval in, the 5-6 year period.
Well, okay.
Dan, hi, I'm Susanna Makovsky. I'm joining CCALS in January.
Susanna?
Thank you for the presentation. You mentioned that, there are people here in the community who are interested in advancing technology or participating in research. And you had talked about, recruitment, and that this research now is being done in the home. So who are the people who are interested in being part of this research project? And, if people express interest in doing this, what is the information that the team needs to know to connect you?
Sure.
You in your group.
So we are, myself and other members, we're happy to talk with anyone who's interested in learning about participating. Most of our participants thus far have been either people with ALS or people with spinal cord injury, about half and half. Some people with certain types of stroke, although fewer of those. And so people who are interested in working with us are usually people who, for this community, for example, have ALS, are interested in learning about the technology, understanding how it can be used. Often they find out about this either through one of these talks, or they find out about it from a member of their care team, their neurologist, their speech language pathologist, their physical occupational therapist. And then once they're interested in learning more, then they reach out to one of us and we have a talk. We chat and we tell them what the research is like. As I mentioned, all of the actual research happens in the home. It is a time commitment. So when people think about joining us, we say, we really, to make this worthwhile for you, and to make this something that would be something we'd meaningfully get something out of, we ask to anticipate that we'll be spending 2 afternoons a week with them in their home. Some of the research sessions are a little, I won't use the word boring because that would be off-putting, but can be a little repetitive, I guess. So a lot of the research is, it comes down to making the system work better. So we have a lot of the advancements are incremental. So outside of our community, outside of our team, there's this big field of machine learning, which are the folks that come up with computer algorithms that listen to patterns and figure out what they mean. And as the machine learning algorithms get better, we want to take the ones that work well and use them to understand how patterns of brain activity correlate to intended movements. And so we'll research different algorithms, we'll integrate them into our system, and then we need to see if they work. So there might be some sessions where we're going to come over our person's home and say, we just want you to control your desktop computer, surf the web, play a game, do what you're going to do. And as you're doing that, use the Braingate system to do it. Let us know how it feels. What does your control feel like? Is it smooth and fluid? Is it easier than other technology than you use? Is it slow? Is it clunky? Is it like trying to use a computer mouse that's too old and kind of jumping around and all jittery? And we may, over the course of a session, try different algorithms. And so it could be like going to the optometrist and say, which looks better, number one or number two, right? Okay, now I'm at number one, number three. And so that can be kind of tedious. Other stuff we'd like to think is less tedious. So we're gonna, work with a robotic glove now. We're going to give you control of different technology. We're gonna integrate this with a software system that's going to, by thinking about different types of movements, allow you to switch between different devices. So right now you're controlling your desktop, and then if you think about squeezing your hand 3 times in a row, all of a sudden now you're controlling your smart TV. And if you think about squeezing your hand 3 times in a row and again, now we're going to switch control over your tablet. That way you can control all the technology in your home. And so people sort of enjoy those sort of research sessions where we're exploring new novel uses of the technology. There's also, to the extent that our participants are interested, the opportunity to do a lot of interesting basic neuroscience as well. So our participants, through collaborations that we have worked on studies that explore how the brain stores new memories, what the brain does during sleep. And these are, everything we do is always at sort of the discretion of our participants. We propose things, and if they want to do them, then we do them. And if they're not interested, then we move on to the next thing. But there's a lot of interesting research that happens that our participants get to be a part of. That's pretty exciting and fulfilling for them and us.
And the follow-up question with that is, the piece of moving all that equipment around is pretty exciting. I think one of the things that is terrifying is having something put in the brain. So, the surgical piece, could you share a little bit about how long that procedure is, or what people need to expect with that component of it?
Absolutely, absolutely, and it's we speak with a lot of people about this, and the surgery is the big part, right? That's the big barrier to entry for many. So the surgery is it's a real brain surgery. So it's a real neurosurgery. The procedure itself, it's about 3 to 4 hours. So you come into the hospital usually the night before. We book the operating room as the first case of the day, which is what you always want when you're having a surgery, because it means everyone's fresh and you've got no delays, anything like that. We go down. In most cases, it's done under general anesthesia. There's the option to do it as an awake surgery. So some neurosurgery is actually done with the patient awake. There are certain types of surgery that actually need to be done that way. This one doesn't need to be done that way, but it's potentially an option. We haven't had anyone do it yet, but most participants are asleep. The neurosurgeon performs what's called a craniotomy. So a small bit of the skull is taken off, put to the side. The arrays are placed with a sophisticated pneumatic insertion device that is sort of gently taps the array with the exact amount of pressure that it's supposed to be tapped with, so that it sits exactly where it's supposed to sit on the surface of the brain. And then everything is done in reverse and closed up, and then they leave. Although the surgery takes about 3 to 4 hours have been in them, and most of it is the way you'd want a neurosurgeon to operate, is really just measuring and measuring and measuring and being very, very careful and very, very precise. The number of physical movements that occur is remarkably few. There's actually very few steps. You could write it out, sort of as I just did. You could describe it in just a few sentences, but the amount of time that is spent lining up exactly where that array is going to go and lining up exactly where that insertion device is going so that it's moving at the exact correct angle for the exact correct distance, comparing what the surgeon is seeing in the surgical field to the images that have been obtained beforehand. That's really what takes the bulk of the time. Then our participants, after the surgery, that they wake up, they spend usually 2 nights in the hospital with us, really just to make sure that they're feeling well. If they have a headache, we're able to treat it, and then they go home. And then the rest, as I said, the rest is done in their home. And then the equipment itself, it's we bring after the participants come home from the hospital, recovered from the surgery, we show up in their home with a rack of computers. It looks something like a remember what those, when people had those big stereos in their home in the 80s and 90s with the different components. It looks like a stereo, like an 80s stereo system with multiple components, and it sits on a little movable cart. We find a place to put it that's not too obtrusive, somewhere out of the way where we can access it. We can turn it on and turn it off without having to climb over things, but it doesn't otherwise get in the way of the flow of the home. And then that's pretty much it. And obviously, it goes without saying, but we supply all of that. No one's buying anything or anything. We bring everything. And the question, I see a question in the chat. How many bulbar onset ALS people have been treated with the implants? It's a great question. I can tell you that we have had, let me just make sure that I'm getting my numbers right. We've had 7 participants with ALS. I couldn't off the top of my head tell you which had bulbar versus limb onset, unfortunately. I know some of them have. I showed you videos of some that had, but we've had 7 participants so far with ALS. Hi, Christine.
I have a question.
Please.
So when you're recruiting people to participate in this study, I get the impression that you're looking for people that are like tech savvy or interested in tech and interesting in furthering science. Are you also entertaining people that are in a stage where they don't have a communication system that's working for them, where even eye gaze has failed them? Is there anyone at that level that you're working with now? And do you want to enroll those people that far along?
That's a great question. So your first point, we don't necessarily require that our participants be tech savvy. They're often the ones who hear about us and are interested. So there's sort of a natural matching of interests, but we're happy to work with anyone who's just interested in working with us. What we find moreover than folks being tech savvy is really people who are looking to find some way to contribute to helping people with ALS. We talk about all of the things that this technology can do, but we emphasize, and I haven't done enough of emphasizing that, so we'll do it now, but that this is still research. And so we tell people who are interested in working with us that because this is research, we can't guarantee up front that this is going to do everything we've shown you, right? It's like when you see those commercials for mutual funds, past performance does not predict, future earnings. These are the things that we can do. We're pretty confident in the way that we do it, and we think that it's going to keep working the way that it's been working. But really, when participants join us, we ask them to think about joining us to help us develop tools that are going to help more people with ALS in the future. And that's the most common unifying theme of our participants. Your second question, which is that about do we work with people who have advanced symptoms? And the short answer is yes, with a caveat, which is that although we have people who have advanced symptoms, including people who use a ventilator 24/7, people who use eye gaze, people whose eye gaze is starting to fail and not as reliable as it used to be, we do still require that all of our participants have at least a reliable way to communicate so that they themselves can provide first-person consent. So there's no surrogate consent. So someone who has lost the ability to, in the opinion of their care team, to provide that first person consent. We at the moment wouldn't be able to work with that person. So they need to be able to because, at least the way that we've framed it for ourselves, because we're asking to take on this risk, because there's a surgery involved, because it has a non-zero risk, but we can't yet guarantee to any one participant that there's a benefit. We ask that they be able to consent themselves rather than a caregiver provide consent on their behalf. But with that said, we have had people who've had such advanced symptoms that they communicate either with eye gaze, or we've had people who communicate with a manual letterboard, where they've lost the ability to move their eyes to reliably use like a Tobii system, but can still blink when a pointer is held over an individual letter. And we'll go letter by letter. And as long as we're confident that they are understanding the risks and communicate them back to us, and we'll spend the 6 to 8 hours to have that detailed conversation, we'll certainly work with that person in a heartbeat.
I have a question.
Please.
If you're already part of a clinical trial, pharmaceutical trial, is that an exclusion criteria for you?
What a great question. From our perspective, no. All my answers are with caveats. So there is no pharmaceutical trial that we would treat as an exclusion criteria. There may be certain pharmaceutical trials that would exclude you from working with us. And so it would come down to which trial, and particularly if you were part of a pharmaceutical trial that required regularly spaced MRIs, for example. So once you have this device in place, you can't have an MRI. And so that would be one exclusion. The only exception would be if there were a pharmaceutical trial that was anticipated to weaken the immune system. That would be the only sort of pharmaceutical trial that we would probably not be able to work with a participant of, because the biggest risk that we think about as being an ongoing participant in this trial is the risk of infection, because there's this foreign object placed in the body. So anytime there's a foreign object placed in the body, be it a hip implant or a pacemaker, the biggest long-term risk is always infection. And so if someone, for example, is on long-term immunosuppressive therapy for an autoimmune condition, that would be someone who we wouldn't be able to enroll. And so if there were a pharmaceutical trial that had that as an anticipated side effect, to my knowledge, there aren't any ALS medications that act in that way. So I don't think that would be a realistic exclusion. So again, come back to the short answer is no. We wouldn't exclude anyone who's in another trial, but that other trial would also have to be okay with us.
And thank you. And a follow-up question: where do you see this technology going in 10 years?
That's a great question. Well, I hope into the clinic is the short answer. So I would love for discussions about this sort of technology to be integrated into multidisciplinary ALS clinics. From a more specific standpoint, there's a couple of places that I think it absolutely needs to go. So I think for this to really become a widespread and more widely adopted technology, one thing it needs to be is fully implanted. So right now, the way that the brain signal is communicated with the system is through that percutaneous component. But there's other types of technology that exist right now that doesn't require a percutaneous connection. So people who, for example, have pacemakers is another good example. They can communicate wirelessly through an implanted bed, so there's nothing sticking out of the skin, and a pacemaker can communicate usually through like one of those magic wands to a computer system that dials it up. Unfortunately, at the moment, we're not there yet, mainly because the signal is it's a really high density signal. So we're recording at about 30 kilohertz from at this point up to 256 channels, and we're not yet able to do that through a fully implanted system. Although that's another, didn't describe it in this talk, but that's another active area of research, is miniaturizing the hardware to the point where it's fully implanted. That's still some years down the line, but I think that's one of the big places where it's going to be in 10 years. I think the things that I've shown you, decoding speech, controlling computer systems, fluid control of software robotics, I think that's all going to be in 10 years sort of off the shelf. It's going to need to be tuned for each individual user, which is an important part of the initial couple of research sessions, is sort of learning for each individual person how their brain and how their brain cells maps to those different movements. But I anticipate that that's going to be something that's going to be a sort of point and click application 10 years down the line. And truthfully, at this point, for the simple stuff, for example, two-dimensional cursor control, at this point, the algorithms that connect the high-dimensional brain activity to controlling a computer mouse, those we can at this point calibrate within about a minute. So when a new user uses the technology for the first time, they're usually able to control a computer cursor like a computer mouse on the screen. We had one demonstration, this was now 4 or 5 years ago, where one of our current participants was invited the first time. We just want to see how quickly they got fluid control. I think it was in the somewhere between 1 and 4 minutes. So that stuff's straightforward. But the more complicated stuff, multi-dimensional reach and grasp with soft robotics, that getting that tuned up quicker is going to be another place that I think 10 years from now we'll be able to do it just as quick.
Well, thank you so much. I'm a patient with ALS, so I really enjoyed the lecture, and I really thank you for what you're doing for us.
Oh, I appreciate it. Thank you so much. Well, thank you, and thank everyone for listening, for the great questions. We learn a lot from working with our participants, but we also learn a lot from interacting with groups like CCALS and other related groups, and the questions that we get really help us think about what directions we should be taking the research, and understanding the priorities of the community is really important for us. We can think about the things that we might think would be really great to do with this technology, but ultimately it's from talking with everyone on this call and calls like this where we learn what's really important for folks. And so it really it helps inform what we do so that we can make this work better.
Thank you, Dr. Rubin, and thank you everyone for participating.